Hello everyone, myself Devashish Das, Assistant Professor of Electronics Communication Engineering Department of Greater Kolkata College of Engineering and Management. Analog Electronics 1. This course is mainly for diploma students of Electronics and Telecommunication Engineering of third semester. The paper code is ETCE AE1S3. Welcome to another sessions of my video lecture. In this session, we will discuss the semiconductor formation. That means how the semiconductor is being formed and what are the types of material is being used to build up the semiconductor and what are the properties of the semiconductor. We will discuss one by one in this session. Before start this session, we will cover up these topics in this session: introduction to semiconductor, classifications of material, semiconductor materials, and Fermi levels. We will discuss one by one in this session. Before go into the deep of this session, here we can see the periodic table. The periodic table is the properties of each material is tabularized form. Each material is tabularized in this periodic table depending upon the atomic numbers of each material. It is the Dmitry Mendeleev who formed and founder of this periodic table. The periodic table is the important table to characterize chemical properties of the materials. In the semiconductor, we can find here it is the silicon and germanium, which is the group 4 element is used for the semiconductor material. The silicon and germanium, which is group 4 element. The semiconductor materials can be classified in the following slides. You can see how the semiconductor is classified, but these are the few semiconductor materials. It is the silicon and germanium which is the major semiconductor material, and it gallium, aluminum, indium, phosphorus, arsenic, antimony, they are all semiconductor materials which is also been used for the semiconductor material. We'll discuss one by one. The semiconductor can be classified into two major classification. That is, first intrinsic semiconductor, another is extrinsic semiconductor. The extrinsic semiconductor further be classified as N-type semiconductor and P-type semiconductor. The extrinsic semiconductor is the impure semiconductor, whereas the intrinsic semiconductor is pure semiconductor. We will discuss the semiconductors in this classification chart. The intrinsic semiconductor means pure semiconductor. That means where there is no impurities present. But in extrinsic semiconductor, there are some impurities in the semiconductors. We will discuss later. The extrinsic semiconductor is further classified into P-type semiconductor and N-type semiconductor. We have to keep in mind the intrinsic semiconductor is the pure semiconductor and extrinsic semiconductor is impure. That means some doping has to be done in the pure semiconductor. So we have to build first the intrinsic semiconductor, then after we can build the extrinsic semiconductor. Silicon and germanium are the two pure semiconductor which is used in the semiconductor industry. It is the sand. The source of the silicon is the sand. That is why it is readily available and it is so cheap. We can process this sand into silicon with the help of some chemical process. In this picture we can see how the sand is being processed in various steps and we can get a pure silicon wafer or the pure silicon semiconductor. And in this section you can see how the sand is being processed step by step to build the pure silicon wafer or the pure silicon, we can say. In this way we can turn the sand into a pure silicon wafer or the pure silicon in this process. It is the Oct rule. Oct rule states that the elements gain or lose electrons to attain the electron configurations nearest noble gas. The noble gases are most stable element because they have a full valence electron cells. All elements want to be stable like noble gases. That is why there are ions. If elements give up or gain electrons, it has a better chance to being stable like a noble gas. We will discuss this Oct rule because we are going to discuss the silicon atom structure. The Oct rule is important and it states the stability of the atoms or the elements. Every elements want to be stable like noble gas. This is the most important rule. Another thing, the covalent band or the covalent bond. Further, the covalent bond is the nothing but it's a electrical bond which is formed due to the sharing of electrons. The electrons share between themselves to form this covalent bond and form the Oct, or the, in case of fluorine we can see this is the fluorine atom, two fluorines, and they share two electrons to make their electron in the octet state. That means there will be a 8 electron in the outermost cells. In case of water, there is also a covalent bond between hydrogen and oxygens. As we know, hydrogen has 2 atoms, so there will be 2 electrons in the outer cell and they are stable, and the oxygen also share 1 electrons from each hydrogens to form 8 electrons in the outermost cell. In this way they form the covalent bond and try to stable at most at possible. So in this way the covalent bond forms. These are the examples of the covalent bond, and we have discussed the octet rule. So now we move to the silicon atomic structure. So it is the silicon, we can see the atomic number is 14. That means if we arrange these electrons, the outer cell has the 4 electrons. The silicon atom has 4 electrons in its outer orbit or outer cell. These 4 electrons, we can see a silicon crystal lattice which is being formed with the covalent bond of sharing of electrons with neighbor silicon atoms. In this way, each silicon form octet or has 8 electrons in its outermost shell with the help of electron sharing with neighbor silicon atoms. So this is the important thing of the silicon crystal lattice. You can see how the covalent bond is being formed in the silicon lattice to stabilize the silicon lattice. This is the most important thing. So a pure silicon or the intrinsic semiconductor, the semiconductor is pure form known as the intrinsic semiconductor. That means there is no impurity. Pure germanium, pure silicon, these are the examples of the silicon or the pure semiconductor or the intrinsic semiconductor. At room temperature of electrons equal to the number of holes. We'll discuss in our coming slides. So we can see the silicon, it is the silicon, it shared the electrons with neighbor silicon atom. When the temperature comes or the temperature is there, the electrons break out and it's moved from the covalent bond and it's become a free electron. You can see it is the free electron which is break out or comes out from this covalent bond, and there will be a gap of electron. We can find a gap of electron. This gap is known as the hole or the deficiency of the electron. This gap is occurred due to the escape of this electron from the covalent bond, and this escape of the electron happens due to the heat or at room temperature. When there is sufficient energy is present to break this covalent bond and bring the electron free, the absence of this electron produced by this vacancy of the electron known as the hole. When there is a hole, so there is a vacancy of electron. So electron is the negative charge and the hole is the positive charge. As the electron comes out from the covalent bond and there is a vacancy, so there is a deficiency of the electron. Now we will discuss the energy band of a intrinsic semiconductor. It is the energy band diagram. It is the valence band and it is the conduction band. There are two bands in the semiconductor, and the difference between this conduction band and the valence band, it is known as the band gap of the semiconductor. And there is a Fermi level situated in just middle of this conduction band and valence band. What is Fermi level we will discuss in the coming slide, but this is the energy band representation of a semiconductor. So we will discuss of the Fermi level in the coming slide. So Fermi level or the Fermi level energy is the energy level above which the probability of finding an electron is 0 at 0 degree Kelvin. In semiconductor, all the electrons have energy less than the Fermi level at 0 degree Kelvin. There are no electrons exist above Fermi level at 0 Kelvin. But if the temperature is going to be increased, then the electron can be found above the Fermi level. that means for 0 degree Kelvin, here we can see in this slide, for 0 degree Kelvin all the electrons are being kept in the covalent bond, so there will be no free electrons, all the electrons are kept in the covalent bond. And for above the 0 degree Kelvin, due to the thermal excitations, the covalent bond breaks and the electron comes out from the covalent bond and it's become free. In this way, at 0 degree Kelvin all the valence band are filled up with electrons and there will be no electron in the conduction band for 0 degree Kelvin. But if the temperature goes up, the covalent bonds break and the electrons comes out, and the electrons are also coming out from the valence band into the conduction band. It is the important thing of a intrinsic semiconductor or the pure semiconductor, where there is no impurity present. So, but if the temperature goes increase, then the electrons can be found above the Fermi level. So we can find the electrons in the conduction band, which is above the Fermi level. Fermi level is the energy level lies somewhere between the conduction band and the valence band. Its positions between the both bands is decided by the donors and acceptors impurities. The impurities will be discussed in the later on slides. Here we can see the band diagram. Here we can see at 0 degree or absolute temperature 0 degree K or 0 K, the Fermi level lies in just between the conduction band and the valence band. At 0 degree K all the electrons are present in the valence band, so the probability of finding the electrons in the valence band is 1, we can see, and in this way we can represent the Fermi energy level. It is the energy gap, Eg is the energy gap, it is the energy gap, and the Fermi level is just in between or middle of the energy gap, so it is energy gap by 2, and it is the functions of the energy, probability functions. You can see all the electrons are present over here in the valence band, so the probability is 1, and in the conduction band is 0 for 0 Kelvin temperature. It is the context of the Fermi level for a semiconductor. We can express this Fermi level with the help of mathematical representation. It is the expression of the Fermi level. Density of states tell us how many states exist at given energy E. The Fermi function EFE specifies how many of existing states at energy E will be filled with electrons. The function Fe specifies under equilibrium conditions the probability that an available states at energy E will be occupied by an electrons. It is a probability density distribution function. So it is the mathematical representation of the Fermi level. EF is the Fermi energy or the Fermi level. K is the Boltzmann constant. The value of the Boltzmann constant is 1.38 into 10 to the power joule per Kelvin minus 23, or it can be represented as 8.6 into 10 to the power minus 5 electron volt per Kelvin. T is the absolute temperature at Kelvin. The unit of the temperature is Kelvin. So this is the important formula of the Fermi energy function we can see, and with the help of this we'll do some mathematics. But before end, we'll discuss some animation video of this pure semiconductor. Let's have a see.
Reality. So let's pretend that they're a flat sheet like that. Each silicon has 4 bonds. And now let's zoom in and look at one individual silicon atom. You can see it's in group 14, so it has 4 valence electrons. And if I heat it enough, then one of the electrons might move into what's called the conduction band and leave a hole. Now, it isn't a literal hole, but it's called a hole. It's the lack of an electron. Shining light of the correct frequency on the silicon may also do this. Going back to our silicon lattice, as I increase the temperature, the electrons in the covalent bonds vibrate more and more until, at a certain temperature, electrons will go into the conduction band, leaving holes behind. Once they're in the conduction band, they are freer to move around and will jump from hole to hole. As you heat the silicon more and more, the amount of electrons in the conduction band will increase. Now, their movement here is pretty random. But if you were to apply a potential difference or a voltage, that is, make one side plus and one side minus, the electrons will migrate towards the positive charge and away from the negative, and that's conduction. So the hotter a semiconductor such as silicon is, the higher its conductivity. Now that's different to metals. As you heat a...
Now we are going to discuss some problems depending upon this Fermi energy. It is a first problem. The Fermi level of potassium is 2.1 eV. Calculate the velocity of the electron at the Fermi level. So here it is the formula of the in this problem, or the EF is the Fermi level, and we have to find out this velocity. So we just rearrange this formula to find out the velocity. We'll just simplify it. Here we just put the value, these two. The value of Fermi level positions is given. It is 2.1 eV. So it is 2.1 eV. We'll just put it, and it is the mass, and we just calculate this and we get the value of the velocity. So it is the one kind of problem. We'll discuss another type of problem. Evaluate the Fermi functions of energy kT above the Fermi energy. Given the Fermi functions, we have to find out Boltzmann constant is, we all know, it is the constant. Kelvin temperature is 300 K. Formula, it is the very well known formula. So just we put the value, we solve solution, we have the formula, this is the formula, and we put, then in this way you can see we just put the value and we get the functional value. It is the desired answer of this problem. Thank you for watching. If you have any queries, you can contact to me. The contact number is given. The same number can be used as WhatsApp number. If you have any queries or doubt, you can call me or WhatsApp me to this number. Thank you very much.